All right, thank you so much, everyone, for coming. So I have the very creative title of Neuroscience, Empathy, and AI. I'm very proud of that title. um, I'm from California, born and raised in California, and I jointly work at UCLA, which is on the left, and at USC on the right. Um, but I'm Indian ethnically, and my family was from Bangalore, so it's always been just such a treat to come to Bangalore and to see my very large extended family here. And these are just many snapshots of all the time we get to spend together. And so it's great to be here and to see everyone here today too. And so I wanted to use this talk. I know that the center is pretty diverse culturally, and there's a lot of intersection between art and some of the technical elements as well. So I'm going to use this opportunity to blend both of the art and the science, and starting with talking a little bit about the work that I do. So I consider myself to be a cognitive neuroscientist, and typically that involves using a series of different methods that are commonly called brain mapping techniques. And so you can see on the left and the right, those are functional neuroimaging scanners. This is typically how we image the brain. We also use a combination of non-invasive forms of brain stimulation called transcranial magnetic stimulation, which is on the bottom of the image. And all of these methods are really targeting more of the systems approached ability to look at the brain. And our aim is to really, at least my research background is focused on humanistic or positive neuroscience. And so often when we think about neuroscience, we think about neuroscience in the context of studying neurological conditions or pathological conditions, but positive or humanistic neuroscience flips the script a little bit to also focus on the things our brain does right. And so there's a lot of pretty amazing, and I would honestly say very beautiful things about the brain, including the fact that we are sort of wired to interconnect with other people. We have empathic capabilities, which really leads to the title of my talk, that very key word in the title called empathy. And my research goal has really been to understand how we empathize as human beings. How is that represented in the brain? And also to understand what empathy is. And so you can have empathy for oneself. You can have empathy for other people, so more of this collectivistic and societal element of empathy. And also my talk will span the empathy that we now intersect with non-human agents as well, getting into the artificial intelligence side of things. Because empathy is so multidimensional and it's a very broad construct, it spans many different domains. Often in the literature, we divide empathy into two main components. So one is called affective empathy, which is more of the feeling. So feeling what someone else is feeling, not understanding. Cognitive empathy is more so the ability to understand and think about what someone else is thinking or feeling. That's how we broadly divide it, and we can map out these distinct systems in the brain. But I think like the most basic definition, the way I think about empathy, is that I'm a human being, you're a human being, and empathy is the mechanism that allows me to understand you. I can't get into your head, you can't get into my head, but it's the closest way that we can connect as a species. So that's really the focus of this talk. I've divided it into different acts to be a little bit more artistic. We don't often call it acts in our field, but I thought act is a nice term. And so in the first act, I'm going to talk a bit about how empathy can be bounded and pretty selective, and understanding how that's represented in the brain. And then act two will be aimed at trying to improve this selectivity that we have in human beings. Are there ways that we can shape it, reshape it, be more malleable? And then in Act 3, I'll talk about selectivity as it applies, as I was kind of alluding to earlier, as it applies to non-human agents as well, going beyond our speciesism. So I really like this visualization because it gives you a good sense. These are called circles of care. And often we start with ourselves at the very center. And our circle of care extends to our family, to our friends, to our community, to our country, to humanity, beyond humanity, to non-human species, to animals, and then to the planet. So it can really extend in all these different ways. But I think the core component of all of these concentric circles is that in our brain, we have these systems that interconnect us, that allow us to do these things. And so I'm going to first talk about this system, starting with these neurons that were discovered in the brain. They're called neuroneurons. And these are very special neurons. When they were discovered, they were considered to be analogous to the discovery of DNA in neuroscience. It was a very profound discovery, also very hyped in a lot of ways, but a very kind of profound discovery in the field. And essentially what they showed is they were testing these regions in the brain, these neurons in the brain, in a part of the brain called the motor cortex. The motor cortex is a region that generally responds to motion. So whenever you do a movement, that brain region will be very engaged. And neurons within that cortical region will also be very engaged. What they found that was very interesting was when they were recording initially in macaques and monkeys, what they found that was very interesting was when the macaque stopped moving, it was just observing the experimenter. Suddenly the system started going a little crazy, because when you hear the neuron firing, it starts to suddenly like speed up and you'll very clearly audibly hear it. And the experimenter is very confused because they're recording in the motor cortex, but suddenly they're getting this activity and the monkey's not moving. And then they discovered that within the motor cortex, there are these special neurons that respond not just to motion, not just whenever you do a movement, but also whenever you see someone else doing a similar goal-directed movement. And this discovery was later extended beyond monkeys. So monkeys are one of the few primates that can do this. These special macaques can do this, but also later to human beings. And so we're one of the few species, along with some very advanced primates, that have these neurons. Core idea is that you have a neuron found in the motor cortex, responds not just to myself, but my brain is wired to also encode you. It responds to my movement and to visually seeing you. And so that clearly has a lot of implications for empathy, because if we were so individualistic and solipsistic and had this very kind of selfish tendencies, as we often think that we do as humans, our brains would never be hardwired to encode someone else. We want to preserve space. We don't have a lot of space in the brain. We have very heavy compute power, and yet we have this ability. So that to me was a very profound discovery. It was the system, and it's the link between the self and the other. And really throughout systems neuroscience, what they've shown is that the mirror neuron system doesn't act alone, and on its own as a system, it's also been very controversial, but in concert with a bunch of different systems, including this higher level system called the mentalizing system, concomitant interactions between these two systems are thought to really prescribe and procure our sense of social reasoning and social connection. The key component is that whenever I think about someone, whenever I do something or think about myself, I'm engaging interactions between these systems. When I also think about someone else, I'm also engaging interactions between these systems. And so the same neural machinery that I use for myself to think about myself in my brain is also being used to think about you. So maybe this doesn't seem very profound at the moment, but it is very profound, because it means that as human beings, we're not very dissimilar. We're using the same mechanism in our brain to think about me and to think about you. So I think this has a lot of implications, and we'll talk about the AI side, but it has a lot of implications for getting down that road as well. And probably everyone knows who this is, but this is René Descartes, and it's a very famous quote, I think, that everyone knows: "I think, therefore I am." And I just want to say it's a very kind of outdated view of what we know about the brain. This is a very solipsistic and individualistic view of the world. But what neuroscience has really told us, and from what I've been kind of saying earlier in the talk, it seems that as human beings, we are more collectivistic, and it falls more in line with these more Eastern forms of thinking. Not to be reductive, not to just say Western versus Eastern. There's a lot of diversity within both. But in general, the Eastern sense of philosophy and mythology and religion, there tends to be this idea that the self and the other are more integrated and more united. And so I have a little thing from the Upanishads where the individual self, it's called Atman, is identical or very integrated with the Brahman, the universal reality. And I'm not going to get too into this because I know I'm not the expert. I think everyone here is more of the expert on this, but there's a lot of things from these cultures that really can shed light on the fact that human beings are very integrated and our brain is representing us that way. So while these are very old cultures, very old things, more new data is telling us it seems to be falling into this route. And it's not just Western versus Eastern, it's also many different cultures. So in South Africa, there's the Ubuntu tribe, and this is also a software that I think a lot of people might use, which really means I am because we are. The concept of Simbo, the self is seen as part of a continuum. Mayans, the self is part of a larger cosmic order with the individual seen as interconnected, not just with other people, but also with nature. And also with Mother Earth and various other tribes across the Andes as well. And I think what's really important to keep in mind is beyond the external component, we share this internal mapping. And I just keep hammering that point, but I think it's a really important point that we see from the research. So thinking about empathy, there tends to be, at least in the US right now, we're in kind of a climate in which empathy has been, to an extent, kind of a controversial term. And a lot of people think about empathy as a very soft thing. They think of it as, why is it important? It's just going to hold you back in certain ways. But actually, again, the science tells us that having empathy and kindness and pro-social tendencies is not necessarily just a benefit for other people. It actually significantly benefits you. And so it's actually wise and smart to be empathic. It's not stupid. Maybe all of you know this, but I think it's just a really important point to underscore. And so there's been various studies, including these interventions, that show that there's been very positive health outcomes for people who give rather than receive kind acts. And so this is not just in terms of self-report, but also in terms of genetic expression. So there's a neuroinflammatory gene called CTRA that generally gets inflamed during stressful situations. They see significant reductions in this genetic expression whenever people do more of these kind acts to others versus when they receive the kind acts. So it goes beyond just self-report and just feeling these things. It also gets into the biology. Okay, and so another point I just want to emphasize is also people underestimate other people's empathy. And so this was a really interesting study in which it was a very large-scale, multi-site study in which people dropped 17,000 wallets all over the world. The wallets had money in them, and they were transparent, so you could actually see the wallet and see the money inside the wallet. And they asked separate people outside of the study to estimate what do you think the rate of return would be. Most people probably said like 40% or 30%. The rate of return was in the 90%. What was more interesting is they thought, okay, well, maybe the monetary amount was $13. So maybe that was just too less. Maybe it's not enough money for people to want to keep. They increased the money to about $100. And they found an even higher rate of return after they increased the money. So this is very surprising because we often think of people as being very selfish and having these tendencies, which obviously society does produce that element. But at our core, human beings, and at least in this study of 17,000 wallets, were very honest about this. So that was very interesting. So it seems like there are many benefits to being empathic. And the question is, why does society struggle so much? So why is there so much of hate? Why is there so much of divide? Why is the government potentially doing things? Why are we in this kind of climate if we're hardwired to be good, hardwired to be interconnected? And I think there's various reasons. And so one thing I think that's really important is that people need to understand that our brains are wired this way. And that's why I've been hammering this point. And again, maybe the majority of people here do understand that. But I think even if one person doesn't understand it, it's an important point to hammer. And we actually did this workshop where I taught inmates in San Quentin, which is a very famous prison. It's a maximum security prison in California. I went to San Quentin and also to California Medical Facilities, which is another prison. Really thanks to my community partner, Martin Figueroa, who introduced me to this entire system. And he's a former parole agent who realized there was a problem with empathy in the police force and then quit, decided to do his doctoral studies to really bring about empathy into law enforcement. And so through these connections, we gave these workshops really teaching people about the importance of empathy and the importance of understanding the neurobiology of empathy. And these are inmates that are there for really horrible crimes. Like, these are murderers. These are just, really the people who've done the worst things on the planet. But they've been in there for so many years. Most of them are they're called lifers. They've been in there for life sentences. They've been in there for like 30 plus years. And all of them, this is the data. I never get data like this ever. This never happens. This was just beautiful data from this workshop. Across both populations, there was all the inmates, the majority of inmates felt that the workshop improved their well-being, improved their empathy. They were more interested in neuroscience after the workshop. They learned something new, and it improved their sense of humanity. And so this was kind of just an early proof of concept and a bunch of things that we're working on in this area, but really showing that it seems like teaching people about these constructs, especially people that are really marginalized in society, seems to have this effect where their well-being and their mindset also shifts. So that was very important. I also included this because I think it's important to hear this. We asked them, what's something you wish more people, outside or inside, understood about how people in prison relate to each other? And they said that we don't look at ourselves like animals, that we communicate with emotional intelligence, that we come from trauma, that we hear our stories in each other. Many people think that we are sociopaths or animals. I did not think highly of inmates until I became one as the result of a DUI death. I have known more genuine people in prison than in the real world. So this is really what seems to happen. So earlier I'd shown you the concentric circles, but it seems like something in society happens where our sense of self really becomes warped and takes over the whole circle. And maybe our family is very important to us, but everything else, maybe our friends too, but kind of disappears. And so I think that's something that we're trying to understand more of in terms of the science. And a clear example of this is, this is a very beautiful image, as you can see. This is in Los Angeles, where I live. This is part of Skid Row, which is really where the most of the unhoused people live. And it's just blocks and blocks of just unhoused people living on these streets, and very big socioeconomic disparities. And people are honestly homelessness is a very big problem in Los Angeles, and people are very fearful of them. And rightly so, because there have been many crimes against people by unhoused individuals. And at the same time, what's also less talked about is that these are pretty voiceless individuals. They don't have a voice at all in society. They're the most marginalized populations that exist. And if you look at, these are just some of the headlines I took recently, only from Los Angeles, so not even across America, just from Los Angeles. And you can see that there's, been murders of unhoused people. They've been beaten up for no reason, stomped, struck by cars. Strikingly, there were 24% of the city's murder victims were unhoused individuals. And homelessness has steadily increased in the last, since 2015 in Los Angeles, significantly increased. What's more grim about these statistics is that the mortality rate has also significantly increased over the years. And what's also very striking about these statistics is that not only has the mortality rate increased as well as the rate of homelessness, but the homicide rate against them has also significantly increased. So it's not that these mortalities are just due to natural causes, there also seems to be murders against them. So really we aimed to, this was a brief study I'll talk about, we aim to use strategies from social neuroscience and social psychology to see if we can rehumanize our perceptions of unhoused groups in the general population, and to identify the strategies that might be particularly important in order to do so. This is in collaboration with the Brain and Creativity Institute at USC and also with Google DeepMind, led by our PI, Lisa Azizadeh, and Antonio Damasio, Srinina Ryan, Jonas Kaplan, and the rest of the team. And this the motivation for the study really to identify the strategies came from looking at work by Susan Fiss, who had identified these two dimensions that people tend to use in society to stereotype different social groups. And so they've done numerous studies across different cultures and populations, identifying that most people stereotype other people according to warmth, how friendly they are, and how competent they are, their skill. And these are orthogonal axes, they're perpendicular. You can see on the y-axis, it's warmth here, competence on the x-axis. And it seems like a lot of social groups can generally be mapped onto this framework. And again, these are stereotypes. It's not vertical, it's not truth. It's just the stereotype that people have in society for these groups. I circled here our focus population. You can see that the lowest of the low, they call them the low, 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 because they are so dehumanized that they don't even, in a lot of the images, they're not even on the scale. They don't even fall on the scale, and that's unhoused populations. So we wanted to take some of these strategies and see if we could apply them in the scanner, if we could actually change brain activity towards these groups and use these strategies to help us do that. And so we had 40 American participants who completed a bunch of surveys before going in the MRI scanner where we imaged their brain. We had a couple of tasks that we gave them, 2 different rehumanization tasks. Rehumanization, we mean trying to rehumanize their perceptions of these groups. I'm going to focus on the static one just because the talk straddles many topics. So just briefly to go into this, we collected their brain imaging data before and after rehumanization. And then we also collected it during rehumanization. Before and after the intervention, we also took their behavioral measures because just looking at brain activity doesn't really tell you much. It just tells you the brain changed. But you always need to associate brain activity with other measures that are either behavioral or self-report, et cetera. And the key component is that in the baseline scan and after the intervention, we actually included high status groups. According to that Fisk diagram that I showed where we had warmth and competence, we included groups that fell very high on that scale, or often stereotyped high on that scale, and that typically includes, at least in America, white, upper middle class individuals. And so we used pictures of them in the baseline scan where people just looked at photographs of these high status groups as well as unhoused groups. And then during the rehumanization intervention, we just had the photographs of the unhoused groups that were associated with different strategies, different texts that we associated with it. And then in the post-rehumanization, we once again included both groups to see if there was a change from post to baseline. So did the rehumanization intervention actually cause a shift in neural activity? And then also could we relate this to the survey measures that we had? And so these were the strategies that we used. And these were taken from social psychology, social neuroscience, anthropology, a bunch of different intersectional areas of research. And we solidified universalism, which is the idea of relating everyone to each other, that you have a child, you have a sibling, that unhoused person has that as well. We also collected participants' own interests and hobbies, things that they liked to do, and we associated their own interests with the unhoused person in the scanner. So their own interest was coupled to that photograph. That was self-similarity. Motor simulation was connecting to this idea that we were talking about with the mirror neuron system, so looking at more of the sensory motor representation through linguistic associations. And then warmth and competence came from that Fisk diagram that I was showing, where we know that those two metrics are very important for how we stereotype groups, and could giving them more warmth and giving them more competence make people feel better towards them. And then we compared all of this to control condition in which they just saw a dot on a photograph. And it's very important when you do these studies that you always have a control condition to compare it to. And so that was just our control. And what we found was really in line with what we hoped. So we found a significant shift in their attitudes towards homelessness after the intervention versus before. We found, and by shift I mean improvement in their attitudes. And we found that this was really grounded in these regions of the brain that are more somatoaffective And so that means that these are regions that are associated generally with feeling. And it's not a one-to-one relationship, but in general, these regions tend to engage during those experiences, and supported by our associations, which shown at the bottom here, associated with our behavioral measures as well. So we felt relatively, all of this is correlational, but we felt relatively confident saying that there was an association between the brain activity and their feelings, their improved feelings towards the unhoused individuals. And when we looked at the strategies during the intervention, we also saw that it really mapped onto what I was showing earlier with the systems level data, the mirror neuron system, the mentalizing system. We really see more of this kind of consistent mentalizing recruitment across all of these strategies, which meant that people are really attributing humanity to these individuals. It's not like they're not mentalizing, right? Because that would be very worrisome. They seem to be doing that, and that was also, again, supported by our behavioral measures as well. So I think all of this, just to talk about that study, was to say that it seems like some of our early work is showing that empathy and prosociality seems to be pretty malleable. That boundary, these are actually, the majority of participants that we had were college students. And college students in general, most of the data shows that they tend to be more compassionate, they haven't been hardened yet by the world. And so they already had pretty positive, not as negative as we would have thought, but still even that positive attitude produced a shift in how they felt towards these groups. And so now we're kind of doing follow-ups to see if we can go more longitudinally and also look at other populations. But I think the important part is that we can change people's perceptions, and seems to be grounded with some empirical evidence from the brain. And also that empathy can be learned. It's not like you either have empathy or you don't. That's a very big misconception. We can always work on how empathic we are. It's always a process. So I wanted to also shift a little bit to some of the next studies, and talk about the fact that I was saying so many negative things about LA, but there's also very positive things, including the fact that it is a hub of music and art and film, and it's a really beautiful entertainment city for that. But when talking about entertainment and music, it's not just about entertainment, it's also used as a tool for unity. And I was reading about this on the way here. I'm really inspired by a lot of the work from India and the previous independent movements and all the things that have come out of the amazing history that India has. And I learned that Gandhi, during the Independence March, sang many bhajans and united Hindus, Christians, Muslims, and united people across the board, all singing these marches to defend India, to gain independence. I learned about Bismillah Khan, who is Muslim, but would go to Hindu temples and play, and to different religions, play the Shehnai. I also learned about this amazing event during World War I, the Christmas truce, where both sides had been fighting in these trenches against each other during the war. But on Christmas Eve, they stopped fighting. They started both singing in German Silent Night and in English Silent Night. And then they came together and they exchanged gifts while they're killing each other. They stopped for that night, used music as a tool to come together and to exchange gifts and to stop this kind of active violence that was happening. So that's kind of the beauty of music, is that it's so universal across cultures. And it's not just in terms of how we feel, it's also, again, it seems to be used in terms of how we can alter our brain. And so music now has become a pretty big, I'm actually in psychiatry as a department, that's my official appointment. And it's become a very big area of research in the field to use music as a clinical tool for many conditions, including neurodegenerative conditions like Alzheimer's or dementia. They're seeing these beneficial effects of music. A good example is the fact that many patients can't remember their basic events in their life or basic facts, more declarative or episodic forms of memory. But when they hear a tune, they can suddenly remember that whole tune. So music is it's a very unique experience for human beings. And sorry, I should say one more thing is that what's really interesting about this figure is that music, you often think about music as it's going to be in my auditory cortex, I'm going to hear it, and it's going to be encoded in my auditory cortex. It's a very kind of sensory experience. What's interesting is that music is actually very embodied and actually tends to engage almost every part of the brain. So it's one of the most unique stimuli to do that, because most stimuli are pretty localized. You do get system interactions. But with music, that's really what this figure shows. It suddenly becomes the whole thing kind of lights up, which is very interesting. So I'm going to play some music just to get everyone feeling it. Thank you. So that music was just Om. That was it. But I think what's really important to understand from that is that in every single person's brain, it was responding very differently to that same sound. So it's a very simple sound. It's just an Om. But the way that each of us respond to that in our brain, we might engage similar systems, but there's a lot of diversity in terms of how we respond and synchronize to that sound. And that's been really shown. It shows that music has this very diverse element, a lot of idiosyncrasies in terms of how people respond to music. And that really inspired the next set of studies that we did. This is with Marco Iacoboni and Previn. She's an amazing musician and songwriter and record producer. Marco is my incredible advisor at UCLA. Julius, who is also a musicologist, who's helping us with the study, and all supported by Renee Fleming and her. She's an amazing opera singer, and her institute and work at Neuroscience and Aspen Institute. And we wanted to see whether we can actually look at how people like music, specifically genres. So everyone has a different genre in general they might like or dislike. So for example, like I hate country music. I'm not a huge country music fan, but I might really like jazz. We wanted to see whether these preferences can actually be mapped in the brain. So can you see this kind of polarized effect to music, these idiosyncratic responses, even when people listen to the same thing? So if everyone is listening to jazz music, but you have someone who likes jazz and someone who hates jazz, would their neural responses look very different? That was kind of the first question. And it's a very basic question, but there's not very much evidence for that question, which was interesting to us. And then we wanted to take it a little bit of a step further and actually see whether we could actually teach them about the genre that they were not as big of a fan of, and expose them to that genre by the musicologist, and see whether later putting them into the scanner, whether their brain kind of reintegrates and rejuvenates to kind of show a more synchronized response to the people who do like that genre. So can we actually reharmonize people's brains in this way? And this was inspired by work in the political domain. And so this is work by Jamil Zaki and his lab. And in this work, they had people look at different, very kind of controversial issues in America. So one of the most controversial issues right now is immigration. And they had people look at the exact same situation related to immigration. And they found that they could really separate, not even knowing who was who, they could separate liberals versus conservatives, even when they looked at the exact same thing. And the way they did that is they used many different techniques, but one of the most prevalent ones is this technique called intersubject neural synchrony, which essentially is just a correlative signal. You just correlate across brains in regions of interest. They focused on the dorsomedial prefrontal cortex, which is a region actually part of the mentalizing network that we were talking about. And they found that they could really map this divergence in these regions between liberals and conservatives. So we wanted to really extend this work and see whether such polarization could also exist in music. The implications of this would really suggest that music could now potentially be a tool starting very basic, but maybe grow to maybe help with polarization across the board. And so this is actually an ongoing study, so I'm not going to get too into this, but we're going to look at these regions, also look at some of the reward signaling regions in the brain, as well as some of the more somatoaffective regions as well that we're talking about. And this just really highlights, again, this is from another study that I thought they had this really nice image because this was just music listening, but they showed you can just see how much of the brain is engaged just when you listen to music. So there's a lot of regions to look at, essentially, for us. Okay, so now I really get into the part related to AI and now the transition there. And I think what really fundamentally separates humans and AI, this is the more recent work that we're doing, is the fact that as human beings, we have many different functions and metrics. But the way we conceptualize our brain is it's not just an isolated brain. We have a body, we have physiological responses, and those are all very integrated. Our brain cannot function without the tight mapping between the brain and the body. And it's a very, very famous term in the field, going back to Merleau-Ponty and early philosophy, which is this term embodiment. And the idea that the brain is dynamically shaped by the body, and it's shaped by environmental interactions, by other people. Our brain is constantly changing. It's not an isolated system. And embodiment has very profound implications with large language models right now because the way that we use models, most of us, I'm assuming, use it in the context of reasoning or in the context of query prompting, question answering. But a lot of the work that they're doing now, and I'm going to show some work at, this is from DeepMind with Gemini Robotics, is to actually make these systems more biologically plausible using mapping, having movement and embodied components, while again lacking the physiological and internal states that we have as human beings. So here you can.
Hi, Apollo.
Hello there. How can I help you today?
I'm traveling to London with my friend next week. Can you help me pack and put the beanie in my bag?
I can certainly help you pack. I will put the beanie in your bag.
And can you tell me if it's going to rain while I'm there?
It will likely rain on several days next week in London, particularly on Wednesday, Friday night, Saturday, and Sunday. I will put the umbrella into your bag.
Thanks, Apollo.
So that's a very basic example, basic in the sense, very basic. What it's doing is very complex, but very basic test of this.
Hi,
I think the key point in these systems is that the area of robotics built upon large language models. So all of their reasoning is, again, built on these systems that we use every day, but embedding the biological plausibility in these systems to have them be embodied, to have them interact with the world around them. And so actually in China, there's huge developments in this area. And so this is actually captured there. You can see this is a dancing robot, which I think is funny. And also they're using them for entertainment. This has become fun to watch, and this is now the time that we live in. And so this work is there's so many goals of all these different companies, including like Tesla's goal of having human helper humanoids in everyone's home in the next few years. Aptronic has Apollo, all of these sorts of different areas, and this is not an exhaustive list. There's a very, very long list of. Recently, we met with this other company at USC, and their robot is actually interviewed here. It's called Sophia. And this is a very different form of a robot because it's, again, built on a reasoning model, but the robot looks very human-like. So it produces almost this uncanny valley effect. And I'm going to play it here so you can see what it looks like.
Robots don't have emotions, and you also said you have a range of emotions. What's your range of emotions?
I can show you.
Okay.
This is angry.
What does happy look like? What does happy look like? What does excited look like? I might be shocked. You said you feel a range of...
So I met this robot, interacted. It was really interesting because it's responding to you in real time. So it's built on the large language model reasoning. It feels pretty natural. Pragmatics is something they're actively working on in this area, but it seems pretty natural. And when you look at the skin and the biology and the human expression, it becomes a very strange experience, I would say. And so that really prompted, I was very curious about this question of embodiment and decided to write this paper on understanding the differences between humans and multimodal large language models. And most of the models that we use are multimodal now. If you use GPT-5, if you use Gemini, most of these are all rooted on, they're trained not just on text data, they're also trained in auditory data and videos and things like that. So they're getting very advanced. They can process not just text as the early models did in the past. I think this is taken from our paper, but really the aim of this, and this paper, I should say, it's also in collaboration with an amazing researcher at DeepMind, Srini Narayanan, and the team at USC as well, with Lisa Zizadeh, Marco Iacoboni at UCLA, and Antonio Damasio. And the key premise of this figure is that the way that humans process information is internally driven. We have internal goals, internal states that really feed our desires. System. Look at this. If you look at this one with multimodal large language models, complete opposite. This is a basic architecture of a standard large language model. You have a modality encoder, which is basically analogous to something like what we do with our sensory receptors. It will take in input, auditory or text or vision, things like that. Taking that kind of input, feeds it one way. There's no bidirectional exchange of information. Feed it to the modality interface, which then goes to the reasoning component, which is the LM. All of this gets tokenized in order for these systems to read it. Very importantly, the multimodal information that gets transduced is not getting transduced in a form of it's actually visual input. It's getting transduced in the form that it becomes tokenized. It just becomes a series of numerical values that the LLM can read and process. Then ultimately, you can have a modality generator that will output its response, or at times you can also output other forms like text or other forms that are non-text, like images or videos and things like that. And there's other forms of multimodal large language models, so vision action language models as well are a big frontier, especially in robotics. But I think the key point here is that it's a very different fundamental process than how we engage as human beings. And so as human beings, we have all of these different components. We have body schemas, we have homeostatic regulation. To survive, we have internal state monitoring. We have interoceptive sensations, which are the physiological experiences that we have that has a very strong role in maintaining our survival. Even breathing is a very repetitive pattern, but it's necessary. So what we proposed here was actually more of a concrete type of proposal for these systems to try to use functional analogs of what we know in humans. And I think it's really important to underscore that we want to make these systems safer. It's not to make these systems human-like. It's not to replicate human emotion, because that cannot be replicated at the moment. It's very fundamentally, uniquely human, that experience. But what becomes very dangerous is the fact that it can feel very human. And so there's been numerous cases. Actually, this was a link from Wikipedia. Now has an entire article on deaths linked to chatbots, because many people, including adolescents, kids, have killed themselves over developing very strong attachments to fake systems that don't have emotion, that don't feel anything, but validate you or make you feel something, and it's not real, it's fake. And they know that. They know that these are artificial systems. So there's something really deeply disturbing happening in this regard. And that led us to this other study that we also did with DeepMind at USC, which was to understand what are the boundary conditions. Why are people, this term is called anthropomorphism, why are they attributing this human likeness to these artificial systems? What are the boundary conditions for why people do this? And so we took the same dimensions that I talked about earlier with warmth and competence, those two dimensions that keep coming up with terms of how we stereotype people and attribute humanity to people. And then we also took the other element that we've been talking about with cognitive and affective empathy, and we prompt engineer these models to have varying degrees of warmth and competence, as well as cognitive and affective empathy. And we had over 2,000 human LLM interactions and 115 participants spanning different topics, including US history, biology, which were our objective topics, as well as more subjective topics. Participants were randomly assigned to either the warmth and competence condition or to the empathy condition, and they completed a series of interactions with these large language models that varied on the basis of their empathy and their warmth and competence. And what we found was that warmth and competence, just as it does in humans, it predicted how human-like the system was. And so that's really here. We found a big kind of jump from low warmth and competence to medium warmth and competence. So there's a pretty big jump there, as well as from low to maximal. Similarly, we found that warmth and cognitive empathy predicted all outcome measures. So trust, anthropomorphism, how similar people felt, how useful, all these epistemic factors also played a role. For competence specifically, it's only significantly predicted the epistemic reliability ones. So often we use these systems to get information. And when it's highly competent but not warm, you actually don't really attribute human likeness to that. So that's an interesting perspective, because it seems like there are ways that we can mitigate how much people anthropomorphize these systems by kind of fine-tuning the relationship between warmth and competence, which is one area we're trying to explore. For empathy, we found somewhat of a similar dissociation between cognitive and affective empathy. But we noticed that affective empathy seemed to predict more of the relational components, so more of the closeness, more of the anthropomorphism, the human likeness, and cognitive predicted across the board most of the outcome measures. So we're trying to understand this balance, how we can use these psychological dimensions to prevent these systems from being over anthropomorphized or becoming too human-like. We want to make sure that these can be safe for people and users using them, because it is a very big crisis at the moment. And so this leads to all the next frontiers that we're working on, and not necessarily us, but also the world is working on at the moment. So there's a big shift in world modeling, which is what I was saying is it seems to me like to be a big frontier now is moving beyond the large language model, the very isolated large language model and of that, and looking more at its dynamic interactions with the external world and how people are doing that, including with robotics. Sam Altman also has this more kind of, I guess, like a 5-step process in which he's kind of mapped out the next frontiers for large language models. And I think kind of the next big one is more of these organizational principles of collective behavior. So having more collectivistic systems and how it can run larger teams and things like that, in addition to agentic AI. Also, we want to look at different forms of AI. So how pro-social should these systems be? There isn't a right answer. And I think this is actually great for getting the audience's perspective on this, because we're trying to do the best that we can as scientists who study these topics, but we're in a new time and a new frontier. And so how we do this needs to be really safe, and it needs to be fair. And so that's kind of the question. And I think it's also important, there is a lot of fear around AI and large language models specifically, but it's important to also understand that these systems are integrated with human beings. It's not a unitary system that's separate, it's how we use them. So we have to study the system together, the human and the LLM, not as independent agents, but now the fact that we are becoming almost combined with these systems. So how do we make these things safe? And I think that is it. So thank you everyone for coming. These are my acknowledgements to all the people who are part of these things. I think we want to talk more about AI. I think that's great for also the Q&A. And thank you very much for coming and for listening to my talk.
Oh, I'm Megha Maheshwari. I'm scientist in Indian Space Research Organization. Your talk was very interesting. I have 2 questions rather than one. One is like how you can differentiate that 2 different type of empathies. Is there any cognitive battery test or something? And second thing is related to AI. Is there if I will give a scenario, I will have a scenario, 2 robots are there in an extreme environment, like a space environment or such thing. So in that situation, what will be your opinion to to teach those robots so that they can work functionally, do better? Whether empathy should be very high or like some particular type of empathy should be there in that, such type of thing. Thank you.
Yeah, thank you for the great questions. I'll answer your second question first. So I think it sounded like you were asking about multi-agent collaboration. So when you have multiple LLMs engaging with each other, how do you determine empathic alignment? Was that your question? Or related to that? Yeah, I don't have an answer. It's a very hard question. I think it's all being investigated, and a lot of this information is also proprietary. So not from me, it's from all of these corporations that keep these things under lock and key. It's a hard thing. I think your question is very, very, it's a great question, because we often think about fine-tuning or engineering empathy to the system on its own and how it engages with the user. But there's big frontiers right now in multi-agent collaboration. And so now when LLMs engage with other LLMs, how do you make sure that empathy is aligned and safe and they're not going to try to take over the world, for example, or something like that? All of that is to say I don't have an answer for you. It's a very complicated problem. And I think that it requires just a lot of people. It's not a one person answer. It's going to take a lot of companies and people working together to answer that. But I can answer better your first question, which is the cognitive and the affective distinction. It's a very great question that I didn't mention in my talk. And so I'm glad that you mentioned it because it's important. You can very distinctly, I would actually say partially distinct. You can see partially distinct networks for cognitive empathy versus affective empathy. People do different tasks in the scanner. So when you're being brain mapped, it's called functional neuroimaging because you can do different activities in the scanner while your brain is being imaged. You're not just passively sitting there, you're actually engaging in something. And so you can have people, a classic affective empathy task is to watch someone feeling pain. And so one of the ones that they do very prevalently is they'll have a needle poking someone and they're watching that in the scanner and they're seeing a needle being pricked in someone's skin. And the set of brain regions that are engaged for that tend to be more sensory motor, intersecting with the insula and some of the more subcortical regions like the amygdala, versus cognitive empathy tends to engage more higher level systems like the mentalizing system. And often it's used synonymously with mentalizing. So they'll do standard tasks that infer what another person is thinking to really get at cognitive empathy. The important thing in all of these things is that we don't have an ideal answer even in humans. How much empathy should a human being have, right? We don't know. But I think what's very important in these situations is understanding that there's always a balance between cognitive and affective empathy. If you have too much cognitive empathy, that's often linked to psychopathy, which is very, we don't want to create psychopathic agents. And if you have too much affective empathy, that's linked to a lot of clinical conditions like anxiety and depression. So there is a balance that needs to be there, but yeah, and we can see it in the brain as well.
I'm Akila Kadambi. This is regarding the empathy which you have been talking and doing a lot of research. In Act 2, you showed the homeless people being killed by various chaps. As part of your research, were you also able to collect data on the crazy guys shooting school kids everywhere and then going to religious centers and shooting them like mad? Were you able to collect any data and do some research on that?
We're too scared to go near them. We didn't go near them. No, we didn't. And I think that's a great question. Probably in the news right now, you hear a lot about America, these things happening in America. It's a very dangerous time for people going to school, which shouldn't be the case. We didn't do that, but that's a great question.
Yeah, I have a very simple question. You said there's a LLM in an AI system. Can you map LLM to a brain function or vice versa?
That answer depends who you ask. But the way that LLMs work is fundamentally very different from how the human brain works. Certain things are very similar. So they're based on neural networks, which our brain has different forms of neural networks where what we use to represent information in our environment. But the entire process is a lot more complex in our brain. And the really interesting thing about the brain is the fact that we have so much compute power. It's very evolutionarily complex in terms of how much we're processing, but yet we're not needing as much data as these large language models need. There's significant compute and energy costs to current large language models. So we're doing something fundamentally different. I think that's the easiest way to view it, is the fact that we don't need as much of that power to do it. The other thing that's very different is the fact, as I was alluding to in the talk, is that our brain is constantly interacting with our body. These systems don't have that. They're very isolated. They're just using next token prediction, essentially. Next token prediction is just a sequential, trying to predict the next token using a self-attention mechanism to infer what is most likely after learning from a very large corpus of data during pre-training. Very different from how humans do it at the moment. I would also say, not to get too into this, but there's also a lot of similarity. So, to brain without an LLM. So that's what they're doing kind of in the it's called the soft robotics or developmental robotics. They're trying to to mimic some of the biological plausibility of our brains, because there seems to be something important about the biology as well, which these are all, LLMs are completely non-biological, or silicone and all these other things. So yeah, I mean, there's questions there. If you were to ask me, I would say, I don't want to be irresponsible, but I do think that there is a lot of plausibility there. So.
Hi, a few years back, a group of experts, nearly 100 or 200 of them, issued warnings about AI, saying
Yes.
that it could lead to extinction of humanity.
Yes.
And public intellectuals such as Yuval Noah Harari
Yes.
are consistently critical of the implications of AI. This seems to have created a kind of fear psychosis among the ordinary people, the public. So, how is the expert community, such as yourself, are trying to counter that? And what is your own personal view on AI? Is it good, bad, ugly?
Yeah, I could say that's a great question. I could say that when I started to understand, because I was always studying, I was always adjacent to natural language processing and to work in LLMs during my PhD. It really happened. GPT 3.5, I think, came out really when it was 2022, right as soon as I had finished my PhD. And so suddenly I was kind of seeing it and realizing, like, this is way more powerful than what I had. I mean, I wasn't doing this research. I was adjacent to it. But from what I known about it, it was a lot more powerful than what I would have expected. And then I had an existential crisis. So I was just, I mean, I think so many people had that, but I was very, I don't know. I was just very like, this is completely unsafe. I felt it was completely unsafe. This should not be happening. And I was completely fearful of it. And as you're mentioning, it became a very big thing. So Jan LeCun, Jeff Hinton, all of these big AI people were also going on the safety side and speaking about it. I would say now my perspective is less fearful, but it's more engaged. So I think it's important to, there is fear hyping as well, but there's also due diligence needed. And so I think that balance is very, very important. It's hard for me to say my personal view, because I think I'm figuring it out still. I think what I'm really interested in is making sure that these systems can be safe and can not cause damage, or limit the damage, but also that they can be interpretable. We understand what they're doing. Right now, it's a black box for almost everyone. So I think it's important to understand what it's doing. Also depends on who you ask. So some people see these systems as just tools. That's all it is, just a very advanced tool. I don't view it like that. I view it as something that's much more complex than that.
Hello, my name is Shakil. I work as a clinical researcher at WISA, which is a mental health chatbot. I think with empathy is really interesting because it's a lot of nature and nurture, right? And a lot of research ties it to attention span, some to motor consciousness, like you put forward. My question is, how do you really tie empathy with AI, especially in the context of robotics? Because with a chatbot, it's fairly simple. A person comes from a volatile situation, you teach them a CBT technique, and it's fairly straightforward. But with robotics, I think it's much more manifold.
Yeah, so you're asking, how do we conceptualize empathy in robotics, and how is it different from large language models? Yeah, it's an excellent question. So that's, I think that the way that we understand empathy in the brain, I keep going back to the body, but that's the way that we understand empathy, is that it's actually rooted in sensory motor processing that engages with subcortical structures in the brain. Across all that jargon, what it means essentially is that empathy is not just thinking, it's also feeling, and it involves interactions with the world, with other people, and intersecting with our own physiology. So when I feel someone's pain, I'm not just thinking, or it's not just in my brain, I'm feeling it a lot of the time. You actually feel that pain. And so that's very different from robotics, because they can move. We made this distinction in our paper between external embodiment versus internal embodiment. So external embodiment is the big focus right now in in these robotic agents and in world modeling, which is to understand how these robots can spatially navigate to improve benchmarking on these tasks like spatial navigation, like action planning, things like that. Our paper calls for the importance of modeling internal embodiment, of understanding that. And so internal embodiment is the interoceptive, the internal states, and the physiological markers, which these systems don't have. We proposed not that you want to put these in these systems, but functional analogs that might help. Functional analogs would be something like modeling fatigue or modeling uncertainty principles, things like that. So analogs in these systems that could potentially keep it in a more vulnerable state. So vulnerability is a very big part of this conversation because human beings have this imminent threat of death, that we are vulnerable as a species, right? So we're always thinking about this, whether consciously or not. These systems don't have that. And so adding these kind of like weaknesses and vulnerabilities into these systems are important components that might lead to more empathic processing and these components. But yeah, I think it's a really, really important question. And it's very fundamentally different than just purely reasoning.
Hi, Akila.
Hi, Smita.
I had basically a curiosity-related question regarding your humanizing studies.
Yes.
How long does the effect last? Has there any study been done?
Yeah, so you're talking about the rehumanization one. Yeah, great, very good question. So we actually were continuing longitudinal tracking with these subjects. We actually asked for some post-hoc surveys. We haven't analyzed the data yet, so we don't know. There isn't really much data because this is actually one of the few studies that aims to rehumanize groups in the scanner. There's not many people who have done this. So this is why this work is so, I think it's important because we call it like understanding social inequalities in the brain. And very little work is being done on this. So human beings need to be more pro-social and actually study these things. So I don't have a good answer there, but the hope is that, it would be a longer term thing, but I think we need a lot more testing to answer it. Yes.
Hi, my name is Shashi. I've got two questions for you.
Okay.
One is there is a lot of conversation about neurotypical brains and neurodivergent brains.
Yes.
So when you talk about these kinds of studies or these kind of research projects, how do you sort of, which brain are you sort of modeling? Is this whole divergent thing even a thing or to be something that should be overlooked? The second question that I have for you is, who is representing, or rather who's working towards making humans more humans when tech is becoming more tech, right?
Oh, okay.
So what kind of research, what kind of institutional infrastructure exists in these academic corridors to help humans become more humans?
Nice. That's a good question. So, okay, let me answer your first question first. So, my view is that neurodivergence is the idea that often we study brains, we study neurotypical brains. And so that means that healthy, quote unquote, in a quotation mark, what we constitute to be a healthy brain is the average person who has no clinical conditions. And we compare everything to that normative baseline to understand brain function. Neurotypical is a term that is now used to be more sensitive about differences in the brain. Sorry, that would be neurotypical. Neurodivergent is to be more sensitive about the fact that brains have a lot of variability and variation. So often we say disorder or clinical disorder, but neurodivergence is saying, well, we're comparing it to one normative baseline. You can be divergent and not have a clinical condition. You can just be different. So I think neurodivergence is very interesting to me. There's a lot of it really depends how you interpret neurodivergence, right? Because someone might consider schizophrenia to be a neurodivergent condition, a very problematic form of schizophrenia, and not a disorder, for example. So it really it's a tricky conversation. But I think that neurodivergence is very important as a term, and it's a very important way that we can understand a lot of conditions, including autism, for example. So our studies, everything in the field, we're stuck with this kind of assumption that we're using neurotypical brains. We often only use neurotypical brains in our research. And we average all of these neurotypical brains in order to use that as our condition of interest. The important thing, though, is to keep in mind is that it's always compared to a control condition. So we're always taking variability in neural signal, comparing it to control condition in order to understand. Okay, let me answer really quick so I can because I really like that question. I don't know how to answer it actually. Making humans more human, that has actually been the large focus of my work. That's why I studied humanistic neuroscience. The term is humanistic neuroscience. It's to understand our innate abilities as humans. How can we understand how the brain represents this? We don't know fully. Nobody knows how the brain represents these constructs fully, and yet we're applying it to systems, to artificial systems. So it's very important to understand the humanness. Recently, actually, Jensen Huang, who's the CEO of NVIDIA, he said that to him, the most intelligent human being, I don't know if you saw this, but the most intelligent human being is not someone who does well in the SAT or the test you take in India. It's someone who has empathy, can feel empathy, and can also have some form of technical aptitude, like understand these things and use that to navigate the world and to kind of see around corners, was the language that he used to predict future trends. So it's very, very important that humans work on their humanness to separate ourselves from AI. The first job to be replaced by AI was actually computer science and programming, not the more kind of empathic and human-like components. That's actually very hard for AI right now. So I think it's very, very, very important for us.
Hi, I'm Dr. Amila. I'm a surgeon. So nowadays we're kind of feeling like patients kind of stop trusting us completely already. Like most of the patients will already have Googled their symptom right down to the grade.
Yeah.
They tell us their diagnosis, not even the symptoms anymore. So, and we're using a lot of robotics now in surgery, like from laparoscopy, it's gone to robotic surgery already. So I'm just wondering, your perspective now, do you think people are starting to trust AI over their surgeons, over their doctors, more? Do they find AI more empathetic, more reliable, more trustworthy? How do you see that going, in future?
Yeah, first of all, I'm sorry you have to deal with that. I don't know. I don't know if I can. I don't know, Mom. Can I share this? My mom was showing me something today. I don't know if I can share this. Your chat. Okay. Well, she showed me this chat she was having with her friends, and I don't know. I don't know if I. Okay. And someone in the chat had said, AI is always right. Large language models are always correct. They're never wrong. They're better than human beings. So I think that there's actually very many cases where they're wrong. They hallucinate a lot. It's called AI hallucination. So they'll make things up or confabulate. So, I mean, but in many things, it really depends on the domain of expertise. So depending on what you ask it, the way that you ask it, there's a lot of variability again in this kind of prompting. They can be very correct too, right? And that's the biggest thing for these companies is to work on mitigating hallucinations right now. They want the most accurate information. Where it gets very complex is things like human emotion or empathy. What is correct? Someone asked that question, like what is correct in those contexts? That's a very hard thing to say. But perhaps with clinical conditions, it's I don't know. It depends again. But I would trust my doctor right now. I'd rather trust my doctor. You can use AI as a supplement, but really it's important. We have the experts like yourself. So
Hi, I work in one of the large companies that you were referring to, training these models. But so one of the reasons ties in with some of the earlier remark. One of the reasons why it's hard to align these models is because there are hundreds of billions of parameters and there's no modular structure, unlike our hopefully our brain. What's your take on building AI models which are more modular, is where you could sort of train specific components for specific sort of functionality and then hopefully get an internal peep in? Do you think that's one possible way to forward towards more humanistic AI?
You're saying at the pre-training stage or at fine-tuning? Pre-training? Yeah, I mean, I think what I understand from most of the companies is that they focus on the fine-tuning stage at the moment. I don't know. You know probably more than I do on this. And they'll use some sort of like reinforcement learning with human feedback to correct the model behavior. I don't know. I mean, I think that altering at pre-training would be ideal. The kinds of data that you use to pre-train becomes very, I don't know. I think this is where philosophy becomes very important for human questions. It's not just engineers or neuroscientists or psychologists. It's also philosophers are very, very, very knowledgeable on what are the ethics in terms of how we do this. I guess you would be a better person to answer whether it's feasible functionally, like the implementation. I would say I could answer more on the ethics side. Is we'd need to be very, very careful on how we handle that kind of information. But yeah, very good question.
Hi, I'm Parveen. I work in AI and regulation currently. My question to you is around human brain. The way you explained it, it's more from the functioning of the human brain as a biological organ, you know, in terms of its neurological wiring and embodiment, etc. But if you were to actually look at empathy, vulnerability, possibly anger, the whole range of human emotions and how they are embodied at molecular and cellular and gene level, how do you see the future of such research integrating into human instinct neuroscience?
So you're saying how do we see the emotionality and the empathy in human beings? How is it integrated in which science?
From a gene and DNA point of view.
Okay.
Yeah.
You're saying is it passed down or is it genetic or? Sorry, I'm asking a lot of follow-up questions here.
Definitely from being passed down, but how is this kind of research being integrated into your work today?
Oh, I don't work very much on that side, so I would give you a really bad answer if I were to answer that. I think it's very, very important. So there's always this, someone brought this up, the nature versus nurture question is very important. I study more of how it's shaped, how environmental factors shape these things, like our behavior, our environmental interactions, our relationships. But there's a lot of people working at these intersections, and I think it's very important as well. I can't give you a good answer on that, but there is some level of some genetic elements being passed down. But it's, again, the very, very critical thing that we know from our research is that these things are not hardwired. Even if you started less empathic as a person, you can always develop it. And a lot of people, whether you tried to do it or not, just become more empathic over time. And so it's not something that's kind of fixed or predetermined early on.
Hi, my name is Pawan, and I'm building a mental health app using Jungian archetypes and internal family system therapy module.
Okay.
So as you know, archetypes are kind of universal patterns, right?
Yes.
They have repeated again and again in history. In Greek culture, you can see in Indian culture, you have similar gods. So my question is more about internal embodiment that you were talking about, right? That's the missing piece between AI and humans. And archetypes are one of those ways that are common to every human. So my question essentially is about these archetypes and what are, from neuroscience perspective, what are your views on these archetypes and how it can benefit AI?
Yeah, very good question. I mean, I think human beings have archetypes we have redundancies, right, biologically. So breathing, for example, is a form of an archetype. It keeps us alive. Central pattern generators are the classic example that we learned in neuroscience. Regularities are very important as well. So we always operate to maintain a very homeostatic state of survival. That's how we survive. And everything we go outside of that state, we want to bring it back into this, it's called like an attractor network. We want to bring it back to this dynamical system that's stable. So I think your question is very good because it's, again, these systems don't have the internal embodiment. I think that what I was kind of alluding to in the talk is that there are computational analogs that we can do because these systems, when we think about the brain, it comes from dynamical systems theory. And that's inherently computational. It's electrical and computational. And so I think that this can be modeled. The complexity to which it replicates human beings really depends on the soft components, the soft biology, mimicking those forms. There's a researcher named Anil Seth who's written a really nice perspective piece on this, integrating the limits of machinery in these systems, like what they can do. The limits of what they can do based on their machinery. And the kind of the standard claim is that you do need the biological plausibility as well. The other question there would be, is this safe and responsible? I think that's the other question. And to what extent should we be thinking about these things? So.
I'm Amit. So I work on open source software and hardware.
Okay.
So one of the questions that I have is a lot of the American companies, OpenAI, Anthropic, yes, they're not like remotely open source. OpenAI.
Yeah, they're not open source, yes.
It's an oxymoron. It's not open in any way. In comparison, if you look at the Chinese ones, DeepSeek and the other ones, should we be considering Chinese models as the standard rather than the American ones? Like, what is your take? We're trying to build empathy, but these...
Yeah, but you're asking an American.
But no, putting that aside, as a researcher, would you want your models to be open source? Do you want to see the weights, or do you not?
Oh, definitely, yeah. I think model interpretability is very, very important. So again, I don't work so much on the AI side. Like I work more on the research side. So we're dying to know what these companies are doing. Everything is proprietary. I would say that I have fine-tuned some of these models using open source models, right? So you can have smaller parameter models that are open source, like Gemma, like earlier GPT models, things like that, Llama, Lava. So yeah, I mean, I think our ultimate quest for AI safety is interpretability, is can we actually see what these systems are doing? And not just for safety, but also for understanding the comparison to humans. So yeah, I definitely want to do that. My answer to the Chinese question would be, I think that we need to get American models to be more open source, not just American, world models to be more open source, and hopefully it's not nationally or geographically divided.
My name's Kiran.
Hi.
Hi. Yeah, I think the expanse and the depth of your research is both astute and profound. Has any of your research intersected with consciousness, even though modern science can't fully define consciousness yet?
I'm sad this question was last because I have like a monologue for this question. All of our research intersects with consciousness. It is one of the most pressing questions right now in neuroscience. We have conferences just dedicated to consciousness, and it's actually one of my favorite conferences to attend is this Association for the Scientific Study of Consciousness. We have a lot of competing theories of consciousness in the human brain. Nobody knows how the human brain works, how it turns on. Like how do we suddenly have the ability to function, and what separates us from suddenly going into a coma and suddenly losing that ability? There isn't like a button, there's a lot of variability, and it's a big quest as people want to understand how consciousness arises. So all of this work relates to consciousness, and I think you're probably asking, like, is AI conscious? Like, what are the implications of this? And again, like, that depends who you ask. I personally am of the view that they're clearly not conscious because they don't have the physiological components that are so important for human beings. to be conscious, we need these integrated systems that keep us alive. But if you define consciousness in a very different way, perhaps you could make the argument that these systems are conscious. They can pass the Turing test, right? So things like that.